possible, le musée Redpath qui nous a gracieusement offert la salle aujourd'hui. Aussi l'Organisation pour la science et la société de McGill qui nous a fourni des fonds aussi. Et aussi, je suis sûre que vous allez être d'accord avec moi, merci à Centropole pour le café qu'ils ont généreusement fourni et qui est, soit dit en passant, carboneutre. Je vais prendre un moment maintenant pour présenter mon co-modérateur aujourd'hui, Victor Frankl, qui est un étudiant en doctorat ici à McGill dans la faculté des sciences. Mais bon, Victor est étudiant ici, mais c'est aussi un organisateur et un activiste pour les causes sociales et environnementales.
Yes, thank you very much again for being here. Like Katrine said, I'm a PhD student here at McGill. I'm also a fellow at the Smithsonian Institution. While my science deals more with diseases and global change, I think that as a scientist, it's our responsibility to advocate for science as well as to promote action. And that's what we're all here for. And I think it's wonderful that so many people are here today and other people are very enthusiastic about signing on and checking out the videos once we post them. But most importantly, you know, we want to thank you for being here and for being part of this community of people that are engaged and concerned and want really to work towards action. In this symposium, again, first we need to thank the Redpath Museum for allowing us to have this wonderful space, as well as the Faculty of Science and the Office of Science and Society for helping to support this event, and really giving us the seed money for future events that will happen throughout the next year. We have a set of wonderful speakers that will be presenting from a broad variety of topics, including physicists, climate modelers, geographers, as well as economists and biologists as well. So that really underscore the complexity of the issue, but are all trying to address particular concepts and how to bring solutions to really the most important issue of our time, which is climate change. It's the most important issue because it has to do with local communities, social justice. It's an economic issue. It's an issue of our infrastructure, and it's an issue of biodiversity on the planet, not only for human welfare, but for the welfare of other species that are having to rapidly adapt to what is really what we can conclude as unprecedented rates of global change. So I'll go ahead and introduce our first speaker, Shaun Lovejoy, who's a physicist here at McGill University. He is addressing the climate crisis in a very interesting way. Essentially, without stealing his thunder, in science, we can never prove anything 100% without the shadow of a doubt. We can only make conclusions with the best available data. And in order to make a conclusion about the validity of a particular hypothesis, principally that climate change is a human-induced phenomenon, we need to be able to reject the alternative hypotheses and reject those hypotheses, the alternative being that climate change is a natural process and has very little or nothing to do with human activities. We can reject that hypothesis with a high degree of confidence, and Shaun Lovejoy will talk to us about just how confident we are that climate change is not a natural process, but it's actually driven by human activities.
Alors, bon, la science s'est fondée sur le développement d'idées qui nous aident à décrire notre monde. Ces idées, hypothèses, génèrent des prédictions. C'est pas possible de prouver ou de réfuter une idée avec complète certitude. Mais ce que nous pouvons faire, c'est donner une conclusion sur la probabilité d'une hypothèse. Dans notre cas, l'hypothèse 1, les changements climatiques sont des processus naturels. La deuxième hypothèse, l'hypothèse alternative, les changements climatiques sont causés par les humains. Shaun va nous expliquer à quel point il est peu probable que les changements climatiques soient des phénomènes naturels. Et autrement dit, la très haute probabilité que ce ne soit pas que le soleil qui causent les changements climatiques, comme le plan de nos amis Friends of Science.
Merci beaucoup pour cette introduction et je tiens à remercier les organisateurs, en particulier Victor Franco pour l'invitation et l'organisation avec d'autres camarades. So, I've been asked to speak in English today, which is fine. I usually do things the other way around when I'm in front of a largely francophone audience. I speak in French with anglophone slides, but I'll do the opposite today. So it will be bilingual in that sense. The slides will be available in both English and French if anybody's interested. All right, so what I want to do today is try and look at things a little bit the other way around from what a lot of the scientific community has been doing over the last 10, 20, 30 years, at least 40 years, which is to take seriously at some level the claim, because they haven't themselves taken it too seriously, by groups like Friends of Science. This billboard is actually a response to the Friends of Science billboards that people may have seen. I'll show some examples in a moment, but Friends of Science is a Calgary-based organization. If I say they're funded by the petroleum industry, somebody will probably file a lawsuit for defamation or whatever, so I won't actually say that. But they certainly are Calgary-based, and they've been putting up these billboards around Montreal saying that, it's not us, it's the sun. Anyways, so this is already a reaction by the Association des communicateurs scientifiques. But in this talk, I want to take their theory seriously. It's the sun. Well, the sun is a natural cause. There could be others, internal variability of a complex system. And I want to say, fine, it's a scientific theory, well, then we can test it. I mean, that's what scientists do. We don't always just, try and prove something is true. We often, prove things are wrong. So somebody who's sick, somebody comes along and say, hey, I've got a great idea, this medicine I've got is wonderful. Here's a reason why, it works. You say, that sounds plausible, but actually you can test that. And without understanding anything about the medicine, you can actually just test it, and does it work or does it not work? And if it doesn't work, well, it could, basically, if you prescribe a medicine which is known not to work, that's illegal, and you're actually preventing somebody from taking a medicine that might work. So in our case, it's a way of preventing us from doing something that actually might improve the situation. So, okay. So, rapidly, I'm going to go through sort of some evidence for the warming. I mean, I think the evidence, well, I'm not going to dwell too long on this because actually most of the climate skeptics now accept that there is warming. So, in fact, this is not very controversial even amongst, except for some very extremists. So, but anyway, this will give you a bit of a historical view. This graph here is the famous hockey stick graph, because my pointer isn't powerful enough to see anything. Anyway, okay, so this is 1998, which was the first quantitative attempt to work out, actually this is the northern hemisphere, but global scale temperature actually on a year-by-year basis, and it uses a whole stack of different, they call paleo indicators. So for instance, tree rings is one of them, but there are also, could be corals, ice cores, lake sediments, all kinds of stuff. Anything which potentially has which does have a relationship with the temperature can be used, and there are something of the order of 1,000 different paleo indicators in this series distributed over the northern hemisphere. And so we get an idea of what the temperature has been doing over the last 1,000 years or so. It's called the hockey stick because it looks sort of like a hockey stick, as you can see. And the idea is that temperatures haven't been doing too much until roughly the end of the 19th century, when all of a sudden they have gone way up. So basically what I'm going to be trying to do today is saying, well, what's the probability that that little end there of the hockey stick goes up just because sort of a random fluctuation, or the sun is all of a sudden doing something strange. Okay, even though we actually have measurements of the sun that show that if anything it's been cooling for the last 100 years, but anyway. Okay, so another way of looking at the same data, this is now 3 multi-proxies, I've averaged them here, so what I showed before was just the first one, and then of course they were developed and improved. So I just want you to concentrate then on 125-year periods. Okay, so I've taken the average out, so the curves are varying around 0. Okay, I just took out the overall mean, but the idea is just to give you an idea of the way things are varying. So this is an estimate from 1500 to 1624. Next 125-year period, 1625 to 1749, 1750 to 1874. You can see, you know, there are lots of variations over a whole range of scales. But, okay, that's the way it looks. And then all of a sudden, sorry, those are the multi-proxies. And then all of a sudden, that's what we've had 1880 to 2004. So more recent 125-year period. So it's gone way, way up. And so the question is, what's the probability that that top curve could have just happened by random chance? Well, that's what I'm going to try to answer. So, okay, so it's gone way up. There's another way of looking at it. You could just rank the temperatures since 1850, according to hottest to coldest, and you see that almost all the hottest ones have occurred in the last 15 or 20 years. Another index, I had to have a polar bear, I'm afraid, but it's true that the northern, high latitudes northern hemisphere, which actually includes Quebec, of course, are particularly sensitive to, and the temperatures have gone up more than they have globally speaking, maybe by even a factor of 2 faster. And consequence, of course, is that the sea ice that you can see in these satellite pictures has been decreasing. Of course, it varies a huge amount depending on the season. So this is the low point in September when these satellite pictures were taken. And you can see that there's quite a lot less sea ice, just visually, but actually it's gone down by something like 2 million square kilometers over the last 35 years. Okay, so those are just some of it. All right. Okay, so I mean, I could go on and on. There's just a ton of evidence about this. But okay, so what have the skeptics been saying? Well, so these are the 3 main arguments they had up till something like 2005. Okay, so they said the models aren't reliable. They haven't been verified. You can't trust them. They've said the data, can't trust it. You've got this heat island effect where somebody's put a thermometer 1880. It could be McGill campus, in fact, and then all of a sudden, but over the last 100 years, cities have grown around it, and the cities make it warmer, and so all we're looking at when we say we have global warming is simply the effect of urbanization. So that's one of their criticism. Another one which took a while to sort out was the fact that the satellites were measuring not the temperature of the surface, but the temperature of the atmosphere, the air in the atmosphere. And there was a discrepancy. They were not showing warming the way we were expecting it to based on the ground-based measurements. But anyway, all of these different grounds for skepticism, which are legitimate to some extent, but by 2005 they were all essentially explained. Okay, so for example, the heat island effect is a very small effect. There's a number of ways of showing that. A series of errors were found in the interpretation of the satellite data, so that's now quite fine. In fact, satellite data now strongly supports the fact that things are warming. And of course the models, well, no model is perfect, but in fact you don't need a model to predict that greenhouse gases such as carbon dioxide will warm the atmosphere. So this led to, by 2006, Michael Shermer, who's the character, he writes a column in the Scientific American every month. He's the editor of the Skeptical Inquirer. And he took him longer than many to convince about global warming, but basically by 2006 he says that, okay, because the problem was so complex, you could justify being an environmental skeptic until about now, meaning 2006, but to go any further, is unscientific, in fact. And so we have to make the jump, he would say the jump to activism instead of skepticism. So, okay, so 2006, I would say, is about the limit where you could have some kind of grounds of legitimate skepticism. Okay, so let me move on to, before I look at what's happened since then, let me look on to the anthropogenic theory, just very rapidly. First of all, we have data about carbon dioxide this is from the ice core in the South Pole, actually. Little bubbles trapped in ice cores that can measure the concentration of carbon dioxide. And as you can see, the value has not exceeded 300 parts per million. Well, this shows for 350,000 years, but actually there's other newer cores that take this back to 800,000 years. So it's only since something of the order of 1959 or something that the carbon dioxide level has exceeded 300 parts per million, and now just this year exceeded 400 parts per million. Okay, so what does that do? Well, this was known even from the it was first realized in the middle of the 19th century that carbon dioxide does absorb strongly in the infrared, and that this could have an effect on temperature. The idea is that it's a greenhouse effect, that essentially the carbon dioxide kind of traps the outgoing heat radiation of sunlight comes in, just like in the greenhouse, but then the heat that's what's called black body emission, the heat radiation that's emitted, can't get out as easily as it could before, and so that makes more heat trapped in the system, and the temperature ends up going up. So here, rapidly, is a kind of a history of this, in the first kind of epoch of, I call it anthropogenic warming. You've got Svante Arrhenius in 1896, that actually he was trying to prove that CO2 levels could explain the ice ages. So he didn't do this calculation in order to work out what would happen if we burned a huge amount of fossil fuels, because at that time, the amount of fossil, we burned about 20 times more fossil fuels since then than there was up to that time. So that wasn't his reason, but he spent a year with pencil and paper and estimated that if we doubled the carbon dioxide level in the atmosphere, we would increase the temperature by 5 to 6 degrees. It's actually not a bad estimate, as I'll come back to in a moment. The modern estimates of the order of the IPCC, the International Panel on Climate Change, is now, has in fact always been saying 1.5 to 4.5 degrees if you double the CO2. This estimate was improved to 2 degrees in 1938 by E. Callender. And the other important development in this epoch was Keeling, who developed a new way to measure CO2 and got regular measurements made in both South Pole and Mauna Loa. And the big thing here is that CO2, if you're anywhere near the ground, is extraordinarily variable. You can imagine, because plants and life of all kinds are either emitting CO2 or absorbing it. If you have a factory, if you have your measurement in a lab and the wind goes some other direction, you get CO2 emitted from a factory, etc. So it was terrible problems getting good data until Keeling. And so he was the one who was really able to show unequivocally that the CO2 levels have been going up very systematically. Okay, the second epoch, which is the modern epoch, is the GCM, Global Circulation Model Epoch, these huge computer model stuff. And, so you divide up the Earth into little boxes, cells that the computer can digest, if you like. And in fact, ever since 1979, the or some of the earliest results were saying if you double CO2, you'd increase the temperature by 1.5 to 4.5 degrees. And actually, just a year ago, September, the 5th IPCC assessment report gave exactly the same range. And in fact, the range, in fact, has not changed. And why is that? So we've had huge improvements in computer technology, algorithms, and all kinds of stuff, but there's rather large uncertainty in the actual value. And the reason for that is feedbacks with water vapor, clouds, radiation. It's a non-trivial scientific problem that has not been solved, and the models have not made significant inroads in that sense. Okay, so we're kind of at so what I'm arguing now is that we're in a moment of kind of diminishing returns in terms of investing in trying to prove anthropogenic warming. So for example, the IPCC4 report in 2007 said it is probable that human influence is the dominant cause of warming observed since the mid-20th century, and the IPCC5 just upgraded that to extremely probable, extremely likely and extremely likely actually in English. So, okay, so we're just more sure than we already were, basically. Okay, so, right, so, and I could just add perhaps that when they use the term extremely likely, they say it means 95 to 100% sure. Okay, so they're not going to get more they're not going to get more sure than that. Okay, at the same time though, what's happened to the skeptics? So I noted, okay, some of them are just, denying everything, okay, fine, but most of them have moved on a bit, and this is what they've been up to lately for people. This is the signs on the top are ones that you can see, say on the Trans-Canada Highway near Anjou. There's one Drummond and St. Catherine that's actually a video version, an electronic sign. There's a campaign, in fact, across Canada. And the one below is actually one that is at the Ottawa airport. Okay, so I already mentioned the friends. These signs concentrate on two things. First of all, the top one is, it says very clearly that the warming is caused by the sun. It's natural, it's not you, it's not CO2. The second one is an argument about what's called the pause in the warming. I will come back to that. They claim that the warming stopped 16 years ago, 1998, and therefore since we've kept on emitting CO2, that proves that the warming is not anthropogenic because in fact it's stopped. Okay. So what I'm claiming now is, okay, this theory is implausible, but it wasn't in fact disproved until this year. So this was a paper that came out in April. Just sort of for amusement here, this was just on Friday. I got this thing from the publisher Springer. Turned out this publication was #1 out of nearly 1,000 in terms of mention index. They've come up with a new thing anyway. So we got a lot of press. A citation index tells you how many other scientific publications cited. And of course, it just came out a few months ago. Not very many will have done. But they have a mention index which is supposed to quantify how many newspapers and blogs and tweets and things. Anyway, so it got a lot of attention. And I'll come back to the reaction of the skeptics in a moment. But, okay, so I want to try and disprove this theory they have. So let's take a look at the data since 1880. So the best data I have is 1880, 2004, and I extended it later 2013, but anyway, this was the main focus. So you can see here, the top graph shows you how does the CO2, actually I call it forcing, because we understand pretty well that the CO2 is going to increase the energy per time coming from the sun to the earth. And so I've plotted what that is as a function of the date, starting in 1880. And then below that, I plotted the global average temperature. Okay, so you can see the basic shapes are not so different. And in fact, whoops, okay. So what the idea was is that I could use the, instead of looking at the temperature as a function of the date, I should look at it as a function of the amount of forcing, the amount of energy per time coming in due to the CO2. So, of course, you say, fine, well, CO2 is only one issue. There's also methane, for example, right? Which is also a strong greenhouse gas. Another thing, so that also will increase the temperature, but there are also aerosols, pollution, brown pollution, which is going to reflect light back into space. So if you do, so that actually have a cooling effect. And that's actually extremely difficult to work out what it does, because not only does pollution directly reflect light back into space, but it also seeds clouds. You get more clouds, and the clouds also reflect. So it's a cooling effect. So this is very complicated. The modelists themselves don't agree about exactly how to handle that. And so I just said, fine, CO2, we have all this data shows that it's very strongly correlated with economic activity. All these effects, land use, methane, pollution of all kinds, it's all strongly related through economic activity. So to a first approximation, if you double economic activity, you're doubling all the effects, okay? And so that was the idea here. So we take, okay, so here's the temperature series again, and these are some, okay. So here is what I plotted as a function of the forcing. So you can see it's looking pretty straight. So it means it is indeed a linear relationship. And if you find that actually the slope, saying if you double CO2, then you actually increase the temperature by about 2.3 degrees. There's a bracket there, but it's more or less right in the range of the accepted values. And you can see that there's some of the different regions I want to talk about. Particularly, you could take a look at 1992, pre-pause warming, and then pause cooling. If you plot that relationship back to date, the temperature is a function of date, then you see this. So you can see that the residue, the difference between this black curve, which says the anthropogenic part, and the red part, which is the natural part, okay, that gives you an idea. And you can see the overall warming is about 1 degree here since 1880. Now, if I show the same graph as before, you can see the residues. That's if I take out that black curve and the CO2 part, the anthropogenic part, then you can see what's left over looks very similar to what we had before. Okay, so the last thing you have to do to test this is to say, well, what's the probability? So how do people do this type of estimation? Standard thing is to use the bell curve. I'm not going to give you a bunch of math on this. If people have the math, they may realize that if you have a 5 standard deviation event, it's like 1 in a million. It's extremely rare. So the warming is in this part of the curve up here. Okay, so if you blow up the curve, so now you're blowing up this is instead of a linear, it's actually log linear. And now you can see that actually you've got the fluctuations in the temperature according to the paleo record are far stronger. You have much more extreme events than you would expect if you had a bell curve. Okay, people have known this, but we were able to quantify this, and we could bound it between these two, this orange and red curve, and we found that actually the extremes are probably about 1,000 times more likely than you would expect if it was a bell curve. But if you just think about that for a second, instead of being 1 chance in a million, it becomes 1 chance in 1,000. So it's still extraordinarily unlikely that we've had this 1 degree increase in temperature just as a random fluctuation. Okay, so actually they call this type of stuff black swans, because a black swan, of course, is an extreme event. If you think all swans are white. Okay, so this was another thing that came out in the summer about the pause. So you can use the same methodology to try and explain the pause. The problem with the pause, what they call the pause is, okay, so it's the fact that over here, the upper right-hand side up there, things are kind of flattening off. The yellow curve is the actual data, and the other curves are some of these global climate models. And what you see is that global climate models have tended to be a little high. Okay, there's about 100 of them there, and some of them are actually fine, but they tend to be a little high. So that means they predicted the temperature is a little bit higher than it has been. So that's the pause. And if you look at over here, then you can see again that just before the pause, there was this huge rise, 1992 to 1998. And if you just look at the part that's left over when I remove the average, this is just the natural variability part. You see actually this 1992 to 1998, what I call a pre-pause, is actually quite a bit stronger than the so-called pause part. So the idea is that you have this huge natural fluctuation, pre-pause, superposed on anthropogenic warming. And then you've got, if you just look at the natural variability, which is what this represents, then you've got a kind of return to the long-term trend behavior. So the pause is actually quite predictable. If you, instead of using a global climate model, you use a stochastic model, which is my area, then you can see that the black curve, and then these are just different probability levels, these other curves, but the black curve, I just superposed, goes almost perfectly through the yellow part. So in other words, you could vary, it's exactly what is expected, in fact. It's just a return to the long-term behavior. Okay, so how did the friends react to these various papers? So first of all, the April paper about the probability being 0.1%. Within 48 hours, they got in touch with they claimed to have got in touch with the Chancellor of McGill and asked him to remove the press release from the site. And they particularly didn't like the fact that in the press release, I used the term denier, climate change denier, or négationniste in French, which of course is what they are. This is kind of interesting. This is from the Facebook site of the Association des communicateurs scientifiques, just after this sign thing came out. And they point out that, the friends, here it is, so it says that the goal, in our opinion, the sun is the main direct and indirect driver of climate change. That's, in fact, the entire organization is set up around that in 2002. And I thought, for this is kind of fun for people. Après les créationnistes, voici les autruches patentées. So obviously they were laughing at this, but yeah, anyway, okay. So another reaction was by a British climate skeptic, fairly well known one, called Viscount Lord Christopher Monckton of Brenchley. And within a couple of hours, actually, of the press release, he was already blogging on this, and he called this this paper, he said it was a mephitic ectoplasmic emanation of the forces of darkness. So this was his, so he's a, you could tell he's an aristocrat with a background in classics, right? Ancient Greek and Latin, so he knew how to turn a phrase. He doesn't know much climate science, but he's kind of made a career out of going around the world telling people about climate science in the last 50 years, paid by various climate denier organizations. But I think it's worth, so there were two main things that came out, including in the Friends of Science press release. It's on their site if you want to check it, but there's two things that I want to make quite clear because, it's worth being able to understand exactly what my claim is and distinguishing it from what they are saying. There's two things. One is, okay, they're saying, there were, they talk about Minoan warm period, Roman warm period, medieval warming, vineyards in England in the 12th century or whatever. We're saying, yeah, well, there were these past epochs where things were just as warm as today or warmer. Well, that may in fact be true, but that's irrelevant. My claim has to do with rapid changes, not slow changes. Changes in 125 years and not, say, over 1,000 years. Okay, so that's one thing. The other thing is they came out with this number. They said if you look at the center of England, there's this series, famous series actually, that from 1663 to 1762, showing there was a 0.9 degree change in temperature. And, that's the same order as what we've had for the whole globe. And so therefore it's a purely natural thing. The only thing is they forgot that central England is only a tiny part of the world. So they're confusing a local temperature with a global temperature. And over that period, the global temperature only changed by about 0.2 degrees, which is totally, not at all an unusual event. So the key point that I'm making is we're talking about a large global change, and we're talking about a rapid change for a century or so. Very rapid. Okay, so I'll move on. Just my last bit, which is, I made about some of the my take on what is to be done, if you like. we know about the consequences to some extent, but the main point is, so this is a graph showing all the different consequences and how they increase as a function of the temperature. This is where we are today. Just make the point that the Stern report, which was tagged by the Wall Street Journal, has said, these are terrorists. The Stern report, I think the Wall Street Journal called it terroristic because they talked about stabilizing the CO2 at 550 parts per million, but this is already quite a bit higher than what we should be having if we want to have a safe climate. But this was justified, but we have to have a stable economy, that's more important. And of course, if you actually look at the scientists, Hansen and others, saying, well, we should be at 350 parts per million. Okay. So what is to be done? So we clearly have to decarbonize the economy. 80% of the world economy at the moment is fossil fuel, energy, I should say, is fossil fuel. And there's a tremendous link between economic growth and fossil fuel consumption. And I just want to rapidly make this point that, unfortunately, there's a lot of what I would call magical thinking going on amongst a part of the economics community. And that is that, they say, fine, just have to make the price on carbon high enough and we can do anything. Laws of nature are no obstacle. And so they are having all these scenarios. This is from the IPCC, actually. Having all these scenarios where you would have 2 or 3% growth per year to 2100. That means 5 to 10 times the economy then as now, and still be able to somehow solve the problem of CO2 emissions. And and if you look at these graphs, the gray areas, that is the part of the fraction of the energy in 2100 that would have to be generated by technologies that don't actually exist. But that doesn't faze them. They say, fine, we just need a carbon tax or something and we'll be there. But I don't think things are so simple. And if people, some of you may be old enough to remember when this came out in 1972, limits to growth, but there actually are physical limits. I'm a physical scientist, and there are physical limits. And what the conclusion of limits to growth is that there's a phenomenon of overshoot and collapse. And there was a paper just September 2014 by Graham Turner, who compared the business as usual predictions of the 1972 model with the last 40 years of real data and found that we were tracking it almost perfectly, and that means that collapse should be starting next year. But okay, so that's one thing. Is growth possible? That's okay. That's out of my area of specialty, but I think that it's unlikely that we can continue exponential economic growth and maintain the climate. But is it desirable? And I think that's something, though, that it's much easier to answer. And if we just look at the last 20-odd years, 30-odd years of statistics from Quebec, you see that, this is actually Canada, that we've more than doubled the gross domestic product, but almost all of that has gone to the top, let's say it's 20%, it's actually the top 1%, and so almost all of us, the median income is more or less the same. So we've been burning all this fossil fuels, destroying the environment in all kinds of ways, and almost none of us have seen any positive outcome from that. And if you like, you can use, instead of using the gross domestic product, you can use the genuine progress indicator, which just tries to take into account some of the negative aspects of growth, such as pollution, could be unemployment, or it could be using up the natural resources. And so this is actually a global study, 20 different economies. What you find is that after about 1975, the higher the per capita GDP, the lower the actual index genuine progress indicator is. That means that we've actually been getting poorer. And there's also a negative relationship between, after about $7,000 a year per capita, the higher the GDP is, the poorer we are. So actually, it has not been helpful to us. So what is to be done? Well, clearly, climate change is a global problem, and the only solution is collective action at a global scale. Okay? obvious. And unfortunately, as well pointed out by Naomi Klein, climate change came on our collective radars at about the same time as neoliberalism and the economies were being deregulated all over the world. And so, unfortunately, we were on a huge collision course with the dominant ideology about deregulation. And so, anyway, I certainly support all these initiatives, which I think is the only way to address the situation at the moment from the grassroots level. Just before I show my conclusions, I thought this was sort of kind of what we're up against, if you like. And so, okay, so I will stop there.
So we have a couple of minutes. I want to get a temperature, read your temperature, not at all dealing with climate.